Okay, good morning, everyone. I will share the screen soon, and then we'll get going. Okay, I guess all of you can see the screen. So you may recall that this was the last slide of the last class. So we were dealing with the martingale XM and a stopping time capital T, both with respect to the sequence YL. And in that result, we had shown that X sub tau wedge n, as n varies, is also a martingale. And an immediate consequence of that is that expectation of X tau wedge n is equal to expectation X0 for every n. Now the concern is going to how to push this n to infinity. So that's what we will look at today. And suppose we can do that. In that case, we will have, let us say it will be the case when tau is finite with probability 1. That is, probability of tau less than infinity will be 1. And in such a case, X sub t at omega, of course, which by definition is X sub tau, means t omega at omega, that is well defined. So this X sub t capital T is a well-defined random variable. Otherwise, you may have problem defining it wherever T is infinity. Okay, so this is just a comment. So today we will look at certain sufficient conditions which would enable us to take the limit as n goes to infinity, which basically means that certain criteria so that we can take the integration, whether it is expectation is an integration or a summation, that and limiting operation can be interchanged. So that goes by the name of optional stopping theorem. And sometimes it is also called optional sampling theorem. I mean, many of these things have their origins in certain statistical procedures. For example, this one, sequential procedures and things like that. And also they are the word optional or optimal. It is also called optimal stopping theorem. These have certain optimality properties, which of course, unfortunately, we will not be looking at. Okay, let X sub be a martingale and capital T a stopping time, both with respect to the sequence Yn or YL. And suppose this stopping time T is such that probability T is finite, that is T less than infinity is 1. So that will immediately enable us that this X sub T is a well-defined random variable. And second assumption we make is that expectation of mod xt is finite. So the first assumption ensures that X sub t is a well-defined random variable. The second assumption is that that random variable is integrable. So that one can talk about its expectation. Integrable means summable. Since we are dealing with the discrete random variables, here it is summable. And another condition, this is a kind of technical condition, is that limit as n goes to infinity, expectation of xn indicator multiplied with indicator of the set t greater than n. So which means you are integrating or you are summing the random variable xn only over this set, the set where t is greater than n. So that you take the limit as n goes to infinity, that is 0. So if these three conditions are satisfied, then the result asserts that expectation of X sub t is expectation X at 0. So this result is also called optional sampling theorem. Some books might call it optional sampling theorem. They may also call optimal sampling theorem or optimal stopping theorem. Note it down if you want. Okay. So let's look at the proof. So this is something which I had alluded to even earlier. First assumption ensures that x sub t is a proper random variable. So xt at omega makes sense. All right. So moreover, it also follows that if this guy is going to be well defined, then it is also something which this is something which is you can easily check. X sub t wedge n omega converges to x t omega as n goes to infinity. Pointwise, this thing converges for every omega. Of course, all these things, every and all, those who are already familiar with the measure theory will know that this has to be taken with a pinch of salt in the sense that everything happens with probability 1. Okay. So now for any n, what is the difference between xt and x tau wedge n? If t omega is less than or equal to n, obviously both will be same. So in that case, that is 0. And if t omega is going to be greater than n, the second guy would be x sub n omega. So therefore, the difference is xt minus xn on this set. Please note it down if you want to. Okay. Consequently, we can write, I mean, I'm just going from here. It's very obvious that x t wedge n, I have brought it to the other side, and I just writing out this. The second thing is valid only on the set t greater than n. So that is what we have done. Oh, sorry, I don't know whether I gave you enough time to copy this down if you want to. So please. Okay. Now, from our earlier result, we also now know that this guy is a martingale. So, if you, our next step will be take the expectation throughout. So, expectation of this would be equal to expectation x0. That's what we have done here. Note it down if you want. Now, look at our assumption 3. Assumption 3 says that guy, as n goes to infinity, that limit is 0. So we know that this is going to converge to 0 from by assumption 3. And expectation of x sub t is equal to expectation x at 0 is what that is the result that we want. So to complete the proof of this result, we need to show that the middle guy goes to 0 as n goes to infinity. Please note it down. Yeah, that's what I was telling you earlier. So to complete the proof, we have to show that the middle term goes to 0 as n goes to infinity. Okay. Let's go to the next one. So for proving that, so far we have not made use of the second assumption, namely the expectation of mod xt is finite. So now we will make use of that. So we have made use of the first assumption and the third one. So now the second one. So because of that assumption, expectation of xt exists, and expectation of xt by definition is summation k going from 1 to infinity, expectation or rather conditional expectation that of xk given t equal to k multiplied with that probability. So t is a random variable which takes values from on the non-negative integers. Of course, starting from 1 because the stopping time is. Okay. So that implies that in this series, all the terms here are non-negative. In this series, if you take k equal to, let us say, n plus 1 to infinity, that is the tail of that series. The tail of the series, as n goes to infinity, is going to go to 0 because this series converges. And this precisely is what we want. This thing is just you take the expectation of xt, or rather you sum only over the set where t is greater than n. Here, see, k is n plus 1 to infinity. And our purpose was to show that this goes to 0. So this completes the proof. Note it down if you want. There are also certain other sufficient conditions actually which will imply the hypothesis of this theorem. In a problem set, I shall give one such problem. Okay, now as a consequence of this optional stopping time, we will derive one result which by itself is a well-known result, which goes by the name of Wald's identity. Incidentally, many of these, even including optimal stopping theorem, etc., they go through even for continuous random variables. Only thing is, in this course, we are not really using those things. So discrete random variables we are taking. And in the case of continuous random variables, you know that expectation, everything has to be in terms of integration. So all the wordings of the proof we have not really used. Of course, things like that you will have to have integration. Yeah. So the Wald's identity says if y0 is 0 and y1, y2 are independent, identically distributed random variables having finite mean and finite variance. Let's say mean is mu and variance is sigma square. And let S0 be 0 and Sn is y1 plus y2 plus yn. So this is just the random walk starting from 0 and where the summands are IID wise. And t be a stopping time with respect to y such that it is expectation of t is finite. This is a fairly strong condition. Expectation of t is finite. We have already seen in the case of Markov chains, stopping times which are probability, I mean, it is finite everywhere, but it doesn't have expectation. Soon we will see another example, which was in terms of, again, that the time it takes for the process to come back to the original state. Then Wald's identity says that expectation of ST, S sub t, is mu multiplied with expectation t. Mu is the expectation of the summands and expectation of t, which comes to. See, we know that since it starts from 0, Sn itself is a martingale, but it is here, it will not be because the expectation of each yi is mu. You know, martingale means the expectation has to be preserved. So we have to sort of make the corresponding adjustment. So we will take y1 minus mu, y2 minus mu, and things like that, and then add them. Okay, that please note it down if you want to. Next slide you will see. Okay. So put x0 equal to 0 and xn equal to, you take yi minus mu and sum over I going from 1 to n. You can easily see that this is just S sub n minus n times mu for every n greater than or equal to 1. And of course, for n equal to 0, that coincides with this. Because S0 is 0. So you can verify that this xn is a martingale with respect to the ys. And since we are assuming this expectation of t is finite, consequently, probability of t being finite is 1. See, we are going to derive this using optional sampling theorem. So first, we have to sort of go about showing that the hypotheses are satisfied. Excuse me. As a consequence of that, S sub t is well defined, and consequently x sub t is also well defined, and x sub t is S sub t minus mu t. These are simple things to verify. Okay. So we will now go about showing that expectation of mod xt is finite. So this is a sequence of steps. So you need to verify each step. Okay. So take expectation mod xt. So by definition, this is expectation, absolute value of each of, this sum, that is k going from 1 to t. Remember that here yk omega, this upper limit is t omega for every omega. So that you have to sum over k. This will be meaningful if you make this thing that either this is finite or it is infinite, because this is all these terms are, since you are taking the mod, non-negative, so that series will converge if it converges to a finite limit, or it will diverge to infinity. So you can make sense out of this equality. Now, whatever it is, this is less than or equal to when you bring the absolute values inside the sum. And this, by definition, for this capital T can be different for different omega. You can split this into, say this event can be split into union K going from 1 to infinity, where T equal to N and some over that, T over K, sorry. So this is this double summation, N going from 1 to infinity and K going from 1 to N of this. Because you take the set T equal to N. So all the cases which are less than or equal to N, you are considering here. And when you take this double sum is a kind of over a triangular lattice. It is not both going to infinity. And when you are dealing with such a domain, when you change the order of summation, you have to exercise some care. You know that. So when you do that and write it in this fashion, you will get this. And there is a question mark here because this is to be verified by you carefully. This step. Whenever you are interchanging double summation over a kind of triangular region or even integration over a triangular region, when you are changing the order of integration or summation, you have to exercise care. Better to draw a rough kind of diagram and proceed with that. That will help you. You might have learned in your calculus or analysis. Sorry, please note it. Oh, it says you have to end in 10 minutes. I don't know why. Okay, let me try to. Aniruddhan, your thing seems to have. So I don't know. Let's see. Huh? Okay. What is that new share? Stop sharing. Yeah. Can you hear all of you?
Yeah.
Yeah.
Yes. We can hear you, sir.
Yeah. So let us try to quickly. Yeah, this is the thing. Today, anyway, this is going to be a short class, but I didn't.
Sir, I just have a question. So this meeting is going to end in 10 minutes, right?
Yeah.
So we have to relog in again to the same link, right?
No, let us see. Let us try to finish this because we are more or less towards the end. Okay.
Okay.
So I presume you can. Anyway, I will be uploading this thing today itself. Okay.
Okay. So Markov chains 9.
Let us not bother about that. That's n plus 1 if it already n was done. Okay. So note that indicator of the set, this thing t greater than or equal to k is same thing as indicator t strictly greater than k minus 1. So which will depend on only on the first this thing up to k minus 1. Consequently, yk and this guys are independent. So therefore, this and yk are independent. So we can split in this. In this can be taken out of this sum. So when you do that, you have this, and consequently, you follows, since this is finite and this is just a constant, rather this expectation is finite, you have that. So this is finite. So the second assumption of the theorem holds. So verifying the third hypothesis. So use Schwarz inequality. So therefore, the expectation of xn times indicator, that thing is by Schwarz inequality, the whole squared is less than or equal to expectation of xn squared and expectation of this squared, but this is square of this is this itself, and that precisely is probability t greater than or equal to. And of course, expectation of each xn squared is n times sigma squared. So this means expectation of t we know is finite. Consequently, this is finite. And again, the tail of this is going to go to 0 because of this, k going from n to infinity. And that is what we are using. And this. So all the hypotheses are satisfied. So the conclusion follows. And as a simple consequence of Wald's identity, we take symmetric random walk and symmetric random walk, simple symmetric random walk. And there the conditions of this Wald's identity are satisfied. And here Sn itself is a martingale because expectation of each yi is 0. Now you take t, the thing is starting from 0. You take t the first time Sn hits level 1. So it is the first entrance time into 1. So t is a stopping time. And Sn is a recurrent Markov chain. We know that. Consequently, t is finite almost surely. I mean, that is probability t less than infinity is 1. But St is 1, so which is not equal to the expectation of S0. So optional sampling theorem is contradicted, which means hypothesis of Wald's identity cannot all of them hold. So the only guy which cannot hold is that expectation of tau is finite. So expectation of t is infinite. So sorry to rush through this. I just wanted to tell you that today's class is the last class. Unfortunately, we had to cut it short, and I will post everything. And the last, this thing that is the proof of that theorem concerning aperiodic thing, I will write it down and send it to you. So now you want me to extend the session by a few minutes? How do I do it? Any of you, do you hear me?
So you can restart with the same link.
Restart with the same link. Okay. I'll do that.
So sir, I have a question. So
please, just let us go for the